Hi, my name is Scott Simpson, and today we're going to be talking about how to draw Lewis structures. The first thing, Lewis structure, it's a 2D representation of a molecule. A 2D representation of a molecule, and it can actually be related to a three-dimensional shape within our heads, or just give us an idea of what the molecule looks like. Knowing the bonding and the molecular topology is important for understanding how a molecule will interact with other molecules. But there's a set of rules that one has to go through in order to draw the Lewis structure. So the very first rule is you have some molecule with some molecular formula, and you have to determine the number of valence. So determine number of valence electrons. So as an example, let's consider xenon trioxide, XeO3. So we have to determine how many valence electrons these systems have, or this system has. So xenon, what you do is you look at the periodic table, group 1 elements, so along this row, we consider them to have 1 valence electron, group 2, 2. We skip over the transition metals because they're crazy. Then we have group 3, which has 3 valence, 4, 5, 6, 7, and 8 finally. So in this case, we have to know how many xenon has. If we look, xenon's over in group 18, or so in this case, it has 8 valence electrons. So we have 8 electrons plus 3 times, that 3 is for how many oxygens we have. We have to look at what we got. Okay, we got an oxygen. And if we look, we know that it's in group 16. In this column along here, that means we have 6 valence electrons. So 6. So for a total of 26 electrons. The second rule is determine connectivity to the central atom. Determine connectivity to the central atom. And what is a central atom? What that is it's the atom that is the most unique or the least electronegative. So most unique, meaning that there aren't many of them or there's only one of them, or lowest electronegativity. A lot of times this tends to be carbon, nitrogen, in some cases oxygen. But for our example, we got xenon trioxide. So xenon, there's only one of them. That's actually going to be the central atom. So we draw this xenon, and we draw some bonds to it. Now note that in each of these lines, these are each a single bond, they represent 2 electrons. So far we've accounted for 2, 4, 6 electrons. We still got to work our way up to that 26 number. Next, what we do is add valence electrons, starting with the more electronegative element. Element. Okay, and there's a point I want to make here. There's something called the Octet Rule, which means an atom only wants to have 8 valence electrons around. This is only valid for atoms with an atomic number of 2 up to 10. So So follow Octet Rule. For atoms that have a charge greater than or equal to 2, but less than or equal to 10. So these guys can only have 8 valence electrons. Others that are higher than 10, they can accommodate more than 8 valence electrons around them. Sometimes they're referred to as hypervalent. Basically, they have an extended octet, whereas elements that are lower, so hydrogen and helium, they can only have 2 valence electrons. The reason for that is if you look at the valence orbitals that they have, there's only a 1s that's available for hydrogen and helium. So they can only take on 2 electrons. So let's draw this out. We had this as our structure. Let's start plunking some valence electrons around. So if we do that, we have to consider which is more electronegative, xenon, excuse me, or oxygen. Oxygen's more electronegative, so we'll start tossing electrons there. Let's count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We have 2 left. Since all of these oxygens have had their valence full, we have to add them to the xenon. And now this might look strange because if you count, actually this one looks okay, because if you count the number of valence electrons around this system, what you find is they have 8 around them. Okay. Next, what we want to do is we want to limit the formal charge. So we haven't drawn the formal charge on this. We'll explain what that is. Step 4 is limit the amount of formal charge. So how is formal charge calculated? So we're going to give formal charge the symbol Q. And Q, formal charge, is calculated by, you take the number of electrons on a neutral atom, the one that you're considering, minus the number of bonds to it, minus number of lone pair electrons, or non-bonding electrons. So let's calculate the formal charge for our xenon trifluoride. Draw it out. Okay, let's calculate it. Let's look at the xenon first. If we look at the number of electrons on a neutral xenon, we can see from the periodic table that should have a value of 8 minus number of bonds to it. If we calculate, we have 1, 2, 3 bonds, minus number of electrons in lone pairs, 1, 2 on this. So that's going to have a total of +3. So what we would do is we would indicate that that atom has a +3 charge on it. I'm going to do that with a different color. And we circle that charge. Let's calculate what it would be for the oxygens. Now, we could calculate it for each individual oxygen, but if we look at those oxygens, they're under the same environment. So we only have to do it for one. So number of valence electrons and neutral oxygen has, it has 6 minus number of bonds to it. And remember, we're only considering one of them. So this guy has 1 bond minus number of electrons and lone pairs. If we count them up, that's 6 for a total of -1. So what we should do is we should put a -1 charge around each of these oxygens. Now, some books favor to put brackets around a charge system. I don't mind it, but I prefer to see the formal charges explicitly written out by those atoms. There are reasons for why you would want to do it the other way, but I prefer it that way. So now the rule we said was is we want to limit the amount of formal charge. We want to reduce that formal charge. So how can we do that? Well, what we can do is we can take some of these bonds and we can swing them, or excuse me, some of these electrons and swing them into a bond. And let's see what happens to the formal charge when we do that. So now we've made these oxygens inequivalent to one another. So we're going to label these oxygens. We're going to call this one oxygen 1, oxygen 2, and oxygen 3. These are just scripts to denote what they are. Let's calculate the formal charge on our xenon now. So again, number of electrons on a neutral atom, 8, minus number of bonds through, if we count 1, 2, 3, 4. In this case, we've increased that by 1, minus number of lone pair electrons, which is a 2, which gets us to a total of plus, not 3, geez, basic math, Scott, plus 2. So we're at a plus 2 there. If we calculate for oxygen 1, which will be equivalent to oxygen number 3, we get 6 minus 1 minus 6, negative 1, because if you notice, we haven't changed anything. So we end up with a negative. If we calculate the charge for oxygen number 2, we have 6 minus number of bonds, 2 bonds, minus lone pair electrons, 1, 2, 3, 4. We get a 0. If there's a 0 charge, we don't have to indicate it on the structure. Okay, so if we look, we've reduced the formal charge, but we're not at the best possible Lewis structure. What we can do is we can do just what we previously have done. We can swing these lone pair electrons down into bonds, and what that will eventually do is reduce the formal charge. Nature does not like charges. If you can get a 0 charge, that's what it will prefer generally. So if we swing that down, let's see what happens. Almost done drawing. Okay, let's calculate the formal charge then. So we get 8 minus number of bonds, 1, 2, 3, 4, 5, 6, minus 2. That totals 8 minus 8, so 0. The oxygens, we could look at them each individually, but they're under the same environment. We get 6 minus 2 minus 4. We end up being at 0. So this is a quality Lewis structure. It may look strange because if you notice, let's count the number of valence electrons around that xenon. We got 2, 4, 6, 8, 10, 12, 14. This xenon has an expanded octet and can take more than those 8 valence electrons. So just remember, the octet rule is only observed for that second row of elements like lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So this is a quality Lewis structure. The very last step, which is more of just a check on what you have done, rule 5, is double check valence electrons. So you want to just make sure you didn't add or remove any electrons when you're shuffling these atoms around. So let's drop back to our example. Okay, so example, xenon trioxide. So remember, each bond contains 2 electrons in it. So if we count, we get 2, 4, 6, 8, 10, 12. We have 12 electrons in bonds, 2, 4, 6, 8, 10, 12, 14. We got 14 electrons in lone pairs. If we sum that up, we end up with 26 electrons, which is exactly what we calculated in step 1. So we can assume that we have the correct answer. Okay. There are trickier situations than this. In some cases, you have a species that is charged. Let's look at the nitrate anion. So example, nitrate, which has the formula NO3 minus. So very first step, we have to determine how many valence electrons we have. We have 5 for the nitrogen. We have 3 oxygens, each at 6 electrons. And then we have that -1 charge. That means you have an additional electron. So 6 times 4, essentially, we should have a total of 24 electrons. Next, we have to determine the connectivity to the central atom. In this case, it's nitrogen. Draw some bonds. Okay. Next step, we have to add valence electrons to the more electronegative element. If we consider the electronegativity of oxygen and nitrogen, oxygen has a higher electronegativity. We've accounted for so far 2, 4, 6 electrons. Let's count more. 8, 10, 12, 14, 16, 18, 20, 22, 24. And we've run out of electrons. Let's calculate the formal charge on each of these. We do that. Oxygen, so how many valence electrons does a neutral oxygen have? We can look at the periodic table and see 6 minus number of bonds to it, 1, minus number of electrons and lone pairs. We get 2, 4, 6. So a total of -1. So we should indicate that each of these oxygens has a -1 charge. Next, let's look at the nitrogen. And a nitrogen in its neutral form has 5 valence electrons, minus number of bonds to it, 3, minus lone pairs on it. This guy doesn't have any lone pairs, 0. So that totals to be a +2. So we get a +2 on that nitrogen. Okay, previously what we did is we swung some of these electrons down into bonds, and that reduced the overall charge. The problem with this species, this molecule is nitrogen is one of those elements that has to follow the Octet Rule. Previously, our xenon didn't, so we could just keep throwing double bonds in our system, and we weren't violating any rules. In this case, we do have to keep the Octet Rule in mind. So let's just take 1 lone pair on one of those oxygens and swing it down into a double bond, and let's see what we get. Okay, so now let's calculate our formal charge. If you notice, we've made some symmetry inequivalent oxygens. Let's label this one 1, 2, and 3. So those are just scripts to show that they are different. I wouldn't indicate them on an individual exam. So we know that the charge on oxygen 1, 6 minus number of bonds to it, which is 2, minus number of valence electrons, or excuse me, non-bonding electrons, 4, for a total of 0. So we don't have to indicate a charge on it. We know that the charge on oxygen 2 should be equivalent to oxygen 3 because they're under the same environment. We get 6 minus number of bonds to it, 1, minus number of lone pairs, which is a total of 6. We sum that up, -1. So each of these should have a -1 charge. Nitrogen, let's calculate that one. So neutral nitrogen should have 5 minus number of bonds. We're at 2, 3, 4, minus number of lone pairs, 0 on that one, for a total of +1. So we should indicate a +1 charge on that nitrogen. You may be saying, hey, wait a minute, can't we reduce that formal charge anymore by just doing the exact same thing? We can't in this case, again, because nitrogen follows the Octet Rule, meaning it has to have 8 valence electrons around that atom. And if we count, we have 2, 4, 6, 8. Remember, each bond contains 2 electrons, so there are 8 valence electrons around that system. Okay, so keep in mind when the octet is observed and when it is not observed. Thank you for watching, and if you have any questions, please leave comments below. Thank you.